Hi. So I just found out not too long ago that I'm going to be teaching spatial statistics again, and I've been going through my old notes, and I was working through my code that I had before, and I made the discovery that there have been some major changes in the R community for spatial statistics. Map tools, RGDAL, and RGOs are depreciated. This has completely thrown a wrench into my gears for my plan for teaching the class. So I'm going through and I'm finding other content to talk about and go over. And for example, the gstat package. All right, so the gstat package, we're going to be using that for things like interpolation and for spatial dependence analysis. All right, and so this package is pretty juicy. I was surprised. I touched on it before, but I've been going a little bit deeper into it, and it's got some good nuggets in there. You'll see where nuggets come in as like a dad joke, a little bit. Uh, so let's go ahead and use the tutorial that's the vignette from the R package as like an example to help us dig in. And so here is the author of the package or author of the vignette uh, name, and here's where you can get to the package. All right, so what we're going to do, just like in everywhere else in R and spatial statistics, we're going to start with the meuse data set. I don't know why this package is so useful or this data set is so interesting. It does have a lot of features that are good for teaching, good examples, but it's kind of like using the Cars data set or the Titanic data set. It gets used a lot over and over and over. It's going to be used here. So, we'll dig in. If you've looked at anything in R in spatial statistics, you already know the punchline of all the models, but we'll go ahead and just keep rolling with this anyway. All right, and so this is in the SP package, and it's comprised of four heavy metals measured in the topsoil of a floodplain along the river Meuse. And there's some other covariates included. Now, if you're not using SP as your data set for spatial data, you're probably going to be using the SF package. More than likely, you're going to use one of those two. SP is a little bit more complicated, actually a lot more complicated. SF stands for simple features. Um, Depending on what you're working on, you're pretty much going to get driven into one of those two packages. So just give you a heads up on that. The process governing heavy metal distribution seems that polluted sediment is carried by the river and mostly deposited close to the riverbank and in low elevation areas. Uh, The tutorial introduces the functionality of gstat used in conjunction with the SP package. Gstat provides a wide range of univariate and multivariate geostatistical modeling, prediction, simulation functions, where SP provides general purpose classes and methods for defining, importing, exporting, and visualizing spatial data. So we're going to use SP to set up the spatial data, and we're going to use gstat for the statistical analysis of that data. Our focus here is going to be gstat. All right, so gstat provides basic functionality for univariate and multivariate geostatistical analysis, including variogram modeling. All right, so here we're looking for spatial dependence, and then geometric and isotropy. And so that's something that we can invoke when we're doing our variogram. We've got maximum likelihood fitting of parcel sills, which are part of the variogram. Variograms and cross-variogram maps. Simple, ordinary, universal, and external drift co-crinking. So that's interpolation. We have sequential Gaussian or co-simulation equivalents for each of the crinking variates. We have indicator crinking and sequential indication simulation, crinking in a local or global neighborhood. And we also have, and I believe that this is the only package I've come across that has this one, block crinking or simulation for each of the variates. Other geostatistical packages for R usually lack part of these options, such as block crinking, local crinking, or co-crinking, but provide options. So here are some other package options that we have if gstats doesn't provide for us. Uh, GOR, GLM. So the GLM one would definitely be a juicy one to dig your teeth into. And the package fields provides thin plate spline interpolation and covariance functions for spherical coordinates of unprojected data and routines for spatial sampling designed optimization. All right, now this is how I like to set up my workspace. I'm making sure I don't have any artifacts floating around. I don't get blasted in the face by numbers. I prefer scientific notation. I like piping a lot. I always use ggplot and everything. And just I always like to know where I'm at, which is appropriate for geospatial analysis. All right, so let's take a look at spatial data frames. For example, we will look at the meuse data set, which is a regular data frame that comes with the package gstat. So a spatial data frame, what we're going to have spatial geometry that is connected to a data frame. The first spatial geometry is connected to the first row of the data frame. The second spatial geometry is connected to the second row of the data frame. You see the pattern? And so this is how we connect these. And this sets us up to be able to handle things very, very nicely. And so as a data frame, so okay, when we load it, it comes in as a data frame, and we have to set it up as coordinates. So we've got X and Y, which are the coordinates. It's not longitude and latitude, just let you know. There's a special coordinate system for this one. And then we have, the metals, the elevation, distance from the river, and then these other ones, they're also part of it that we're not going to really use. All right, so my first step is I'm going to set up the coordinates of the data frame. So right now, before I run this line of code, it's just a data frame. It's not a spatial data frame. I'm going to set up the coordinates as the X and Y columns, and boom, now I have a spatial points data frame. And the X and Y here define those points. So here is a summary of the object. So we can just see what we've got going on. It's an S4 object. All right, and so we're just taking a look at the first few coordinates of it. You can see that this is definitely not latitude and longitude. All right, well, let's go ahead and do a quick visualization using the bubble function. I like bubble plots a lot, by the way. And so much of the tutorials in spatial statistics has focused on zinc. We're going to do exactly the same thing. And here we've got, we've got the zinc, amounts. So the bigger the bubble, the more zinc there was. And this is going to be along the river. And then, we're going to have a low-lying area right here, if I remember correctly. All right, we can also, the author's code to make sure that the visualization is printed, he did it twice a lot of times. So there's redundant code in this. I know, I just didn't remove it. I kept it just to make sure there wasn't something I missed. But here you see him printing off of the same code he had a moment ago. Note the following. The function SP coordinates, when assigned on the left-hand side, I use arrow notation, promotes the data frame, maybe converts is a better word, may use into a spatial point data frame, which knows about spatial coordinates. Coordinates may be specified by a formula, a character vector, or a numeric matrix or data frame with the actual coordinates. The function SP coordinates, when not assigned, retrieves the coordinates from the object. So here, how we used it was we used the function for assignment. Remember that I had the arrow on the right-hand side of the function, but if I didn't have that arrow or an equal sign on the right, then it would retrieve the coordinates for us. And then once we do this, once it's in a spatial data frame, we can run plot and bubble super easily and get what we want. Okay, so let's go ahead and take a look at it. So now, we can just see what's going on. All right, so here's the meuse grid. So this is for a grid of points. And now I'm going to use a formula to assign the coordinates. Notice that at first I start out with a data frame. I assign the coordinates, and now I have spatial points data frame. And we need to assign that this is a gridded object. And so then, instead of spatial points, it becomes spatial pixels because it's on a grid. And so let's do a visualization of this. And so here I'm using dist from the river. And so you can see that here, this is the closest points to the river because it's along the river, and this is the farthest from the river. All right, so here we can do some interpolation here. Here I'm just doing zinc, via constant. So there's no covariance to the model. And we can see that also gives me a spatial pixel data frame. And when I plot it, so here is the predicted value of for each location. And so this gives me an easy way to, make fit a model and then use that model to come up and make a prediction across the ground. That was easy peasy lemon squeezy on that. So here I'm setting up what the data is. Here I'm setting up what the grid points are that I'm going to have for my prediction. And you'll notice that these don't perfectly match up. When I look here, I've got points that are not sampled in here. Well, the function went ahead and interpolated everywhere in between. Use the model to fill in the gap. And here you can see like that concentration, here and here. The river's coming down, coming across, it's kind of like hitting the shore. It's, moves along, and then comes along, boom, comes up there. All right, and here I'm just printing the same thing I did before. If you compare the bubble plot of zinc measurements with the map with distances to the river, it becomes evident that the larger concentrations are measured at locations close to the river. This relationship can be linearized by log transforming zinc concentrations and taking the square root of the distance of the river. So the author has explored several models and decided that log zinc is better than zinc, first and foremost, because of skewness, which would make sense if we actually ran the data frame. And then also decided to do, equivalently a box-box transform on the distance from the river. And so now let's go ahead and fit that, and boom, look at that. So this is, strong evidence that we definitely want to include, square root of distance in our model. When we do our modeling, we always want to go simple to more complicated. So I'm going to do spatial analysis without doing any, covariates. I'm going to analyze, the target variable with the covariates by itself. Then I'm going to combine the two is how I'm building up. So the previous model I had, that this is modeling just using spatial, because remember, I just had the constant in my IDW function. So there's no covariates in this. So now I have a spatial model, no covariates. Now I have a covariate model, no spatial aspects. Where we're headed is to put them together. And this is how we want to actually proceed in real life, is that we start simple and we progressively get more complicated until we feel like we reach a conclusion. Usually we'll keep it going until we overshoot the mark, then we take a step back to pick our final model. All right, variograms. Okay, so here is a variogram. I copied and pasted this from Wikipedia. Okay, so the variogram is assessing spatial dependence. between points. All right. The variability between the value of the covariates, if the variability gets bigger and bigger and bigger between them, the farther apart they are, that's an indication that when they're far apart, they don't have any spatial dependence. But if that variability shrinks as we have the points close to each other, then that's an indication we have spatial dependence. So when I look at, so on this particular plot, when we look at a lag distance of, let's say, 25 or more, we see that we've reached maximum variation between like 2 points being compared with each other. All right, so if we have 2 points that are more than 25 away from each other, then it's not unreasonable for us to feel that there is no spatial dependence. But look at the left-hand side. Let's say we're looking at points within 5 feet of each other. All right, if we're talking about points within 5 feet of each other, we've got less variation between their observations. And so this indicates that we have spatial dependence when they're closer together. All right. So, I mean, that's a statistical model. All right. So, this is the opposite of IID, right? Because they're not independent because they have spatial dependence. All right. So some things that we need to define in this. The nugget is the minimum amount of variation that we have between observations that are mathematically zero distance from each other. Now, I mean, practically speaking, like as close as they could be in real life. The range is the distance where we believe that we have spatial dependence, and beyond that range is we feel like they're far enough apart that they're spatially independent of each other. And then the CEAL is the maximum variation between the observations. All right, so let's go ahead and use that to talk about the variogram. So keep that picture in your mind as we proceed forward. All right, so variograms are calculated using the variogram function, which takes a formula as its first argument. So we have log zinc with no covariates, means that we're assuming constant trend for the variable log zinc. And so here we're only considering spatial when we do this formula. All right, we're trying to baby step into this, keep it simple. Okay, so here's what we get back. We get back a data frame from this. And we can see the distance, and we have NP and we have gamma. Now, once we have that, we can use the fit variogram function. And now here we have to specify what we believe is correct about the variogram. So remember that I've got the nugget, the CEAL, and actually the order that the function asks for is CEAL, model, range, nugget. So CEAL, it at first asks for maximum variation. They ask for the model of the way that you're mathematically going to compute things. Then they ask you to specify the range. Then it asks you to specify the nugget. Okay, so we're going to set it up. So here I'm going to set up the partial CEAL, set up the model. Here it's spherical, the range, and then the nugget, and then boom, we have the fitted variogram. And now let's go ahead and plot this. Okay, so here, what we have is the variation between the observations that are relatively close to each other, but not the same. So take all pairs of points I have. So if I have, if I've got n points, it's n choose 2. So n times n minus 1 divided by 2 possible pairs. So, a little bit less than n squared divided by 2. Just conceptually give you a size estimate, which is a wrong estimate, but close. I'm going to take all of those that are relatively close to each other and calculate the variation between them. That gives me this point. Now I'm going to make another bucket of distances and calculate. Another distance of buckets, calculate, and keep on doing this until I get this shape here. And so visually, you can visually see what I have of the sill, the range, and the nugget. Now, previously, we had concluded that we needed square root distance from the river in our model. Okay. Remember, I'm baby stepping into this. I'm not going to, just, try to just, dive in straight to the thing. Because, in real life modeling, I would be going through a lot of different models, a lot of exploration, start simple and keep on making it more complicated. Now, I'm going to make it a little bit more complicated by doing log of zinc depends on square root of distance. Then I'm going to fit the variogram. And then for my model, I'm going to put the sill of 1. I'm going to use the exponential model. Range is 300. Nugget is 3. And so now I have this. And notice that now it doesn't look as, it's not matching as well as it did before. But I firmly believe that square root distance needs to be in the model. So I'm going to keep it. Now, I might go through and might actually, in real life, I know I would. I would go through and change the parameters here. I would definitely explore the other models that they have, and eyeball, the data, see if I can come up with a better way to go. All right, so now Kriging. So Kriging is interpolation, and so uh, in this, we're just going to use the Krig function on this. First and foremost, we're going to just have spatial. We're not going to have a covariate yet. Here's the data that I have and now here are all the locate this grid of values is going to give where I want the interpolation to happen. And now I want to get my get this. Here we go. We can see that along the river, we're definitely seeing more. Now this is a more complicated model. You'll notice that there's more heat along the river, and there's more of a contrast here. It was relatively flat comparatively in the previous IDW model that we did. We also do conditional simulation on this, and so we can go through and set up in max and number of sims. So here I'm just doing 4 simulations. And this is a generalized least squares realization. And so now I have the results of my different simulations. And so now, like in these simulations, one thing that's jumping out at me is I don't see those patches of dark area, which is a big switch. So, something to look at, something to consider as I work through all my possible different modeling. All right, so now let's switch it up. So this simulation used ordinary Kriging. We can also do a different version of Kriging. Like here, we're going to use universal. All right. And so now I'm actually, I've got my covariate included. We're basically stepping it up as we go through to get more, get deeper, more complicated, and to get the best model that we can. And so now, now I'm feeling a little bit better about this because here, notice how much darker this became off of this. And so, we've got the model going along. And now, which model do I feel is the right one? It's going to be the one that looks the most like that bubble plot. Remember that green bubble plot I looked at? Whichever model matches that green bubble plot the most is the one I'm probably going to, actually use at work. Now we can also do directional variograms. So something about this, notice that we have a very, very, very strong southwest, northeast directionality of my data. And so we can look at this is that I really have like 2 axes of my actual data. I've got northeast and southwest, but I can also have there's like my major axis, My minor axis is going to be northwest and southeast, going in the perpendicular direction. Okay, cross. And so we can, we can incorporate a directional aspect into our variograms to get a better model. And so I feel like I should do that. So let's do it. All right. So the following command calculates a directional sample variogram where directions are bent by direction angle alone for two pairs, ZS and ZS plus H. The separation vector is H and it has a direction. Okay, so we will classify directions into four direction intervals. All right, and so here I've got 0, 45, 90, and 135. And so I'm going straight north. So yeah, and in this, 0 is north. And we go clockwise. So this is the opposite direction as trigonometry. So we're going is we're working on a compass because we're doing something that is on that's spatial. So like on most visualizations, we put north going straight up, and then we're going to go clockwise. And so 45 is pointed northeast, 90 is straight east, 135 is pointed southeast. And so you can see that I've captured most of the directions if I allow north to also to account for south. I have east also accounts for west because they're opposite directions. And then I have the other two major directions left on the compass. Okay, so when I set this up here, I'm setting up with a 45 degrees on the compass because that's what I believe, what makes sense with the data set. So we have a strong correlation in the northwest southeast direction. No, it's northeast southwest. I messed this up because it should be northeast southwest direction, 45 degrees on a compass. And when we look at this, we look at the length here and the length here of the data. I'm eyeballing that. That ratio is about 0.4. So the minor axis divided by the major axis. And that's how we come up with these two. Okay, so now let's take a look. We look at this. All right. That looks, relatively close. Not as, probably could tinker with the sill a little bit, get a little bit better, but overall, I'm feeling satisfied with the shape of the curve. Just want to bring down the right-hand side a little bit. Let's keep on. So see, this is from Variogram zinc direction. This is the same plot. All right, so looking at directions between 180 and 360, we'll repeat the image shown above because variograms are symmetric in nature. When I look at a distance between points A and B, it's the same as the distance between points B and A. And so because of that, I don't need to repeat myself as I work through. The first plot gives the variogram in the 0 direction, that is north, and 90 degrees is east. So if you got a strong trigonometry background, remember that rotations are in a different direction, and the angle of 0 is like, north is, typically represented as straight up on a visualization. By default, point pairs are assigned to the directional variogram panel with the nearest direction. So north contains everything between negative 22.5 and positive 22.5. So like that. And that's going northwest to northeast. So, if I'm looking north, negative 22.5 is to my left, rotate a little bit, and then 22.5 is a rotation to the right. After classifying by direction, point pairs are binned by a separation distance class, as is done in the usual omnidirection case. In the figure, the partial sill, nugget, and model type of the model are equal to those of the omnidirection model fitted above. The range is that in the direction with the largest range is 45 degrees, and the isotropy ratio. The range in the 135 direction and the range in the 45 direction estimated by eye by comparing 45 and 135 degrees sample variograms. All right, let's take a look at that. All right, so here we've got 135. You can see that's not really that great of a fit, while 45 is a pretty good fit here. So I feel like 45 is the better model to go with. 135, what we would be doing, 135 would be putting an emphasis on this direction, going from northwest to southeast, while 45 is putting an emphasis on going from southwest to northeast. Unfortunately, the gstat package does not automatically fit these parameters for us. We have to do it manually. Uh, all right, so the package author, points out that they do not claim that the model fitted here is best in any sort of way. In order to get a better model, we may want to look at more directions. Just keep trying things that just make sense. And try, different variogram parameters, try different directions, mix it up, you know, see, try to get the best one you possibly can. More elaborate approaches may use directions in three dimensions and want to further control direction tolerance, which may be set such that direction intervals overlap. For the residual variogram from the linear regression model using the square root of the distance from the river as a covariate, the directional dependence is much less obvious. The fitted model here is the fitted isotropic model that is equal in all directions. So the isotropic model is where we're not really worried about direction. The anisotropic model is where we're concerned about direction. And so let's go ahead and take a look. Let's throw in the distance from the river, square root, in there. Let's use those four directions we talked about a moment ago, and then run our variograms. All right, so we've got a little bit of wiggle. So, subjectively, like, I'm not feeling this as much as I was where with the other one. But, so, we need to do like some interpretation, some thinking about which model is better for this. I mean, this looks pretty consistent. The trend is high, but at least it's, following it pretty well. We've got a little bit of wiggle. Which one's better? Which one's worse? That's your call. As data scientist working on the project. So variogram maps, another means of looking at directional dependence in semi-variograms is obtained by looking at variogram maps. Instead of classifying points ZS and ZS plus H by direction and distance class separately, we can classify them jointly. So if H is a point in the two-dimensional coordinates of the separation vector in the variogram map, the semivariance contribution of each point pair is, well, the difference between their covariates squared. And this is attributed to the grid cell in which H lies. So what we're doing here is I'm taking my data and I'm centering my data. I'm taking it and I'm translating it so that now my data is moved so that it's centered on the origin. And so from the center of my data, I'm going to run that analysis because it will be easier for me to interpret. So H is a geographic distance rather than a geographic location now, which is kind of mixing it up. If I'm more concerned with location, I want the way we've been doing it. If I'm more concerned about distance from a reference point, this is the way that I'm going to do it. Cutoff and width correspond to some extent to the map extent and cell size. The semivariance map is point symmetric around 0. All right. All right, so let's go ahead and fit the model. All right, so here, I've got square root distance in there once again using meuse. I'm using a cutoff and a width, and I'm saying, hey, go ahead and map this for me, and let's plot this out. All right, so This looks, different than what we had, but you'll notice that the most important thing that we want to look at right now is that, boom, see that the center of the plot is 0, 0. I have negative x-axis, positive x-axis, negative y-axis, positive y-axis. For this, the thresholds assure that only semi-variogram map values based on at least 5-point pairs are shown. This way, this removes like too noisy estimation. The plot is plagued by 1 or 2 extreme values corresponding to cells with a very small number of point pairs, which should be removed. All right, so we wouldn't actually use this. The author did further analysis that's not shown here, but here we're looking at functioning code so that we would know what to do. We would, the author's comment is just showing that we need to do data prep before we do this model. Now, cross variography, I've got a bunch of models, or sorry, a bunch of covariates in here. Maybe I want to start modeling, all the different covariates like together. All right, so let's go ahead and do that. So now I've got log of zinc, depending on distance from river, log of cadmium from square root distance from the river, log of lead, log of copper. All right, and so I could have done this code in piping, but I decided not to keep it consistent with the author. So you'll see that first, we set up G, and we have nothing prior. Then I'm going to take the output here, put it here, and then that's the new version of it. I take the output that I just made, put it here, that's the new version. And I just keep on doing this. I could have easily done this with piping. It probably would have been a little bit cleaner, but yeah, I wanted to keep it consistent with the author. And so now I've got, a geostat object going, and let's go ahead and run the variogram on that. Then I can run the gstat function on it, and let's go ahead and fit an LMC, and then boom, look at all, and we'll talk more about this modeling in another video. And so, now we have a much more complicated object that has a lot more submodels in it for us. And so, we've got, 4 submodels all coming into play together. And so we can take a look at each of these, and you'll notice that I've got semivariance between the log of the metals and the distances. So on the diagonal, I have the regular semivariance for one variable at a time. The off diagonal, I have the pairs. So I can get the cross semivariance. And we can go through and visualize also what we've got here. See, this is with the variogram. And this is just repeating what we've already looked at. And so this code, the author didn't really talk about too much, but it was there. I went ahead and cleaned it up and put it there. Okay, so we've talked about a lot of stuff. I would say the number one thing to walk away with from this video is how, like a quick, very brief introduction to setting up coordinates for an SP object. The next thing I would say is the variogram. Understanding the variogram, being a feel for it, using that to assess spatial dependence. I hope this video has been helpful. Remember, life is short. Do math.